Hey there, video 29. We're marching right along. This one should be fairly short because it's just sort of expanding on what we did. Nothing terribly new here. Question 1 is review. Nothing here to tell you. Okay, question 2, I did want to give you some advice on general expressions. If you have only even powers, so you would think in terms of 2 to the I or 2 to the n as being that exponent on your x minus a, or your x over here, and this is for even only coefficients. So the thing is, when you're doing these, you still run these guys up from 0 to infinity. You don't like, I would have the instinct to just put the little notation evens only, but that's not how people do it. You actually adjust the expression so that it marches along with still using the integer coefficients. Think about like you're programming a computer. You have to make well, actually in Python you don't have to do that, but anyway, if you want to make things odd only, you usually use 2i plus 1 or 2n plus 1. Now, to be honest, if you said 2i minus 1, you would also get a sequence of odd only, but that is not considered standard. So if you want to make somebody really, you want people to see that you're using just evens or just odds, this is the standard way to accomplish that task. Okay, so I want you to sort of see some tricks of the trade. Let's say your function is e to the x. Then this expansion is going to really just look like, well, you can figure out why it looks like this, right? Because it's just your regular old x to the n over n factorial, and since e to the x is its own derivative and e to the 0 equals 1, all that other stuff over here cancels out. You don't have to worry about it, and then you just see these pieces marching right along, and so on and so forth. Okay, so one of the cool things is you can like take the derivative term by term, and this is a way of showing that the derivative of e to the x is e to the x. So you're going to get x, bring the 2 down, bring the 3 down, and then you get 2 factorial, bring the 4 down, and then you get 3 factorial, and so forth. So you can just see that e to the x is its own derivative. Let's see, what else? Yeah, you can do things like this. You can say e to the x squared and say, well, I don't want to redo this whole thing. What a pain. But I'm just going to replace the x by x squared, and voila, you have this beautiful expansion, and you didn't have to do any extra work. You didn't have to take e to the x squared and take the derivative, which is a pain, you know, because the derivative of that is e to the x squared times 2x, and oh my gosh, I don't want to take the derivative of that thing. Oh, what a pain. So there are all these cool little shortcuts that you're going to eventually learn and become acquainted with, and this is one of them, where once you have this general expression, you can harness it by just swapping something out algebraically, and that's really convenient. Something you need to be aware of when you're thinking in terms of natural log. Remember what natural log looks like. Natural log of 1 is 0. It's a really convenient place to center these things, but we would never, ever, ever center at 0. It has to be something positive. So since it has to be something positive anyway, we may as well center at 1. It's the most convenient place. But you could center natural log expansion anywhere you like that's positive, okay? But again, 1 is the most traditional place to center that, and it ends up giving you a lot of really convenient formulas, and then you can take derivatives and integrals and all sorts of cool stuff right off of that. I wanted to show you this cool trick. We recognized that this was the way we could write sine of x. So let's go ahead and write that. Sorry. Okay, so this is sine of x, and so we hope that we can just take the derivative term by term, and actually we can. The other thing is, notice that these are all odds, right? And when we take the derivative, we're going to end up with only evens. So how's that going to work? F prime is going to be, remember, we're taking the derivative with respect to x. So this negative 1 to the I is just going to stay right there. We're going to decrease this exponent by 1, and we're going to multiply by that over here. But what happens when you have a number, you have a factorial, and then in the numerator and the denominator, in the numerator you have like if you had this kind of thing, right? This is just 1 over 6 factorial because the 7's cancel out, but the rest of that factorial is still there, right? So you end up with 2i factorial, and so that is cosine. And you could have just derived cosine from scratch, but maybe you don't want to. And that's great. And you're like, wait a minute, didn't you just tell me that that was what I would write if I wanted just even terms? And that's true. And this is more generally true. If you take an odd function and you take the derivative of it, you get an even function. And if you take an even function and take the derivative of it, you get an odd function. And you get to see that in the exponents of the terms of the Taylor-Maclaurin expansion. So it's really, really cool. You get to watch that. Now, I want to give you a warning, okay? And I just picked sine and cosine, and it turned out that I didn't have to worry about this I equals 0 term, because when sine of x doesn't have a constant, right? Has no constant term. It starts with x, so the first piece that I see in cosine is 1, right? I see the derivative of x is 1. All right, so there was no problem. I didn't lose anything per se. Okay, but a lot of times, like if I take cosine and I take its derivative, it's going to give me negative sine. And see, what happens is I have to deal with the indexing, which is just kind of a pain. The students don't like it. I think it's kind of cute, but it's not fun when you're worried about your grades, but it's fun when you're not worried about your grades. Okay, so what's going to happen if I take the derivative? I'm going to subtract 1 from the exponent, and this goes over here, this 2i minus 1. Okay, so this is not correct. Why is this not correct? This is not negative sine because we haven't really fixed the problem that at I equals 0, there's nothing wrong here. That's not a problem. But at I equals 0, we're going to get x to the negative 1, and that isn't part of negative sine. It's just a completely bogus thing to do. And furthermore, you're asking me to take factorial on negative 1, and that doesn't make sense either. So this is bogus. So the only way this is going to work is it's going to work if you start at I equals 1. Let's see. It's actually, yeah, it should work if you start at I equals 1. So what happened is that I equals 0 piece you had over here, when I equals 0, the term was 1, and when you take the derivative, it disappears. So this process will be okay if you just adjust the lower index, but now you have a non-standard representation for minus sine of x. At least it's correct, okay? At least it's totally correct mathematically now, and I can breathe a sigh of relief. But you can't publish that. Like, you can't tell your friends to use it or anything. It's just for your own personal use. It's okay, right? But it's going to confuse everybody else because we're used to starting with I equals 0. So we're going to have to do this touch-up thing where we have to make this go down to 0. That means all the other i's have to go up, like I plus 1. And then this I is going to go I plus 1. And then it's going to make all sorts of messes. I swear, it's going to make a lot of messes. I'm not going to do it for you right now. It's way easier to just say, look, you know, if I want negative sine of x, why don't I just add a plus 1 here and I'm done with it because I've just flipped all the signs. That's the easiest way to accomplish that. Okay, but trust me, the algebra is there. If you follow it through, you will end up with this expression now. Okay, about question 3, I'm going to show you something and I'm going to tell you not to use it, but you really ought to know what this is. The binomial expansion of something like a plus b to the 5. Use binomial expansion, and honestly, if you want to fast forward, I'm going to just leave that little star up there. You can fast forward until I get rid of this little symbol, because this is something that you really ought to know, but you don't need it for this exercise, but it really ties in very nicely. Okay, you have to start with Pascal's triangle, and you have to sort of figure out what the coefficients should be. If you have not seen Pascal's triangle, ask me or Google it, but I'm not going to repeat it because I think most of you should know it. And since my exponent is 5, I have to take the 5th row of Pascal's triangle in order to do this expansion. And so then I just go ahead and say, okay, this expands into a to the 5th plus 5a to the 4th b plus 10a to the 3rd b squared plus 10a squared b plus, whoops, third, 5ab to the 4th plus b to the 5th. So that's how I can do that. But that's not what I asked you to do. Okay, so I'm going to now erase this. Hopefully everybody else can join the video. This is not what I want you to do, although you could do it to verify your result. I don't want you to actually use the binomial expansion for that question. What I want you to do is use the techniques of this chapter in order to achieve that result without actually going through that process. That's what I really want you to do. So what you want to do here is you want to say, okay, you have 1 plus x. I'm going to start this for you and let you finish it. This is equal to 1 plus, okay, so we already know the answer because we know how to do this expansion mess. Okay, so we know the answer, but we want to get it by an alternate method. Okay, so what we want to do is say f of x equals this function, and we want to take the derivative of this function, and we want to take another derivative, and we're going to take another derivative, that's the last derivative, and then it becomes 0. Okay, so if you evaluate it, that means f of 0 equals 1, f prime of 0 equals 3, f double prime of 0 equals 6, f triple prime of 0 equals 6. And it's this information that we're going to use to figure out the answer that we already know. Okay, so we're going to see how this ties together. And like I said, I'm getting you started on this, but I want you to use this information and then tie that in. So use your Taylor and Maclaurin process to get back to this answer that we secretly already know is our answer. Okay? So that's the point of that exercise, is not to actually expand it, but to use Taylor-Maclaurin to achieve that result. And my last parting shot is I wanted to just say video 3, I'm just looking at worksheet 3, it's just going to be hints. You actually have all the material you need to finish worksheet 30, and I would encourage you to go ahead and try that before you look at video 30 so that you can see if you need the hints. If you don't need the hints, then you don't need to watch video 30. So there's not going to be new material. But anyway, I will see you either on video 30 or maybe video 31, or see you in class. Okay, bye.